Yaskawa.
The Technical Training Department of Yaskawa America Incorporated presents Harmonics, a guide to understanding and successful control. I'm Steve Kaler, and today we are going to answer these questions. What are harmonics? Why do we care? And when we care, what are we going to do about it? Now, if you're involved with a facility that uses a large amount of electrical power, well, these are very important questions. And there are lots of good reasons that the answers matter. It's essential to have an understanding of how harmonics work and how to handle their effects. So to begin our understanding, let's get down to the fundamentals. All electrical power is distributed as a sinusoidal voltage. Why a sine wave? Well, it's easier to understand that if you look at the basics of how a generator works. At its simplest, a generator is a rotating magnet in a stationary coil of wire. The rotating magnet, or rotor, is called the field winding. The stationary coil is called the stator winding. The field winding, or rotor, is excited by direct current by means of carbon brushes and slip rings. The field winding is turned at a constant speed by a mechanical power source connected to the shaft. As the field winding turns, the magnetic flux sweeps by the stationary stator windings, which induces voltage in the stator windings. And in a two-pole generator, the induced voltage makes a complete cycle of values for each complete mechanical revolution. And what do you have? A sine wave. In a two-pole generator, the frequency of the induced voltage in cycles per second, or hertz, is the same as the speed of the rotor, or field winding, in revolutions per second. The electrical frequency is synchronized with the mechanical speed, and for that reason, this type of equipment is called a synchronous generator. So, a two-pole synchronous generator turned at 60 revolutions per second, or 3,600 RPM, will produce a 60 Hertz voltage sine wave. Power generation in the world today is a three-phase system. So, synchronous generators used for power generation produce three-phase voltages displaced 120 degrees in time with respect to each other. A simple three-phase, two-pole synchronous generator with one coil per phase is shown right here. When an electrical load is connected to the voltage source, it draws current to perform work. If the current follows in the same sinusoidal pattern as the voltage, then the load is said to linearly follow the voltage and, in short, is called a linear load. However, if the connected load does not follow the sinusoidal wave shape of the voltage, then the load is called a nonlinear load. Nonlinear loads cause stress on the transformers and generators that make up the power system, also known as the power grid. This stress has been found to be primarily thermal in nature. In other words, stuff gets hot. And even though the load that is doing the work can be very efficient, the overall energy used to perform the work of a nonlinear load is much higher than a linear load. Power systems carrying nonlinear loads are less efficient. So, it's important to find them and take corrective action to reduce their negative impact on the power grid. Now, in the real world, the grid is filled with all types of devices that create nonlinear loads, like power supplies for computers and electronics, lamp dimmers, variable speed drives. A great many things consume current intermittently, in blocks or bursts, causing the sine waves of the power grid to become distorted. Now, if you're an electrical power utility, distorted current waves are a problem. And, as mentioned earlier, distorted waveforms increase line losses. They stress generators, they overheat transformers, and they can destroy power factor capacitors. The other users down the street who share your electrical grid care as well. Distorted current drawn by your nonlinear load can result in distorted voltage on the grid. Distorted voltage can shorten the life of your neighbor's power line equipment and increase the cost of their power. It overheats their transformers, stresses their switchgear, and increases neutral currents. The greener world also cares about distorted current. because it wastes energy and it increases heat. There is an important aspect to keep in mind when it comes to distorted voltage on the grid. The distorted current that is drawn by the nonlinear load is local in nature and flows only into the nonlinear load consuming that current. However, when distorted current is transported to the nonlinear load, it causes distorted voltage drops all along the power system, which leads to distorted voltage on the grid. Voltage is common to all users, and distorting this common grid voltage can create widespread losses and may result in faulty operation of many types of electrical equipment. In order to reduce the level of distorted voltage, it is important to limit the flow of distorted current. To get a clearer understanding of why this is so, let's use one of my favorite simple teacher analogies and imagine that voltage and current in the power system are like pressure and water flow in a household or multifamily water system. If you are opening and closing the water system of one area, well, bursts of water are coming out. But bursts of pressure are going in the other direction in the system as well. If the bursts are strong enough, the water system of the guy next door, the one that normally flows so smoothly, won't be so smooth anymore. At least it won't until you stop surging the system on your end. So obviously there needs to be a remedy to distorted waveforms on the power grid. But before we can try to fix power inconsistencies, we really need to define and quantify them. As mentioned earlier, a distorted current waveform creates heat in the power delivery equipment. Resolving a nonlinear waveform into its sinusoidal components is called harmonic analysis. Harmonic analysis will estimate the heating effects due to nonlinear currents flowing through circuit breakers and transformers. And that's where this gentleman, Mr. Fourier, enters the picture. An 18th century mathematician and physicist, Jean-Baptiste Joseph Fourier, introduced the notion that even the most complex waveforms could be understood and mathematically defined as a composite of a fundamental frequency sine wave with other sine waves in multiples of that frequency. We call these waves harmonics. Fourier also gave us a complex mathematical equation to define the relationship, an equation that has struck terror into the hearts of engineering students and physics teachers ever since. Right here is a demo of a wave being resolved back and forth between its fundamental wave and the distorted or composite wave by adding or subtracting some of its harmonics. Now we are looking now at how multiple waves can exist in the same system at the same time. By looking at this graphic, you can see that constructing a composite wave is fairly intuitive. For example, if the fundamental wave says go up 6, while the harmonic says go down 2, the result will be a composite wave that goes up 4. Now, deconstructing a highly distorted composite wave into its fundamental and, say, the 20-some harmonics that distorted it is much less intuitive. And this is the math that makes that possible. The ratio of harmonic content to fundamental is defined as total harmonic distortion, or THD. THD is expressed as a percentage of the fundamental. The higher the percentage, the more distorted the waveform. Now, our primary concern is voltage harmonics, since voltage is what is common to all. We have to understand that the only way to limit voltage harmonics is to minimize current harmonics. If the current harmonics are under control, the voltage harmonics are generally acceptable. Theoretically, there are both even and odd-numbered harmonics. Typically, in an AC power system, even harmonics are absent. Our concern here are the odd harmonics, which are present in an AC system and do contribute to total harmonic distortion. Odd harmonics that are multiples of 3 in a 3-phase power system, called triplet harmonics, theoretically are absent in a balanced three-phase system. However, perfect balance is rarely the case, and one must be ready to deal with triplet harmonics that form a noticeable amount of losses in an AC power system. Now that we have a measure of harmonics called total harmonic distortion, the next question becomes, how much distortion is too much? Well, the industry standard is IEEE 519-1992. It defines the acceptable levels of TDD, or total demand distortion, at the point where the customer ties into the power grid, called the PCC, or point of common coupling. And note that we have cleverly changed from THD, total harmonic distortion, to TDD, or total demand distortion. Now, what is TDD, and how is it different from THD? Well, TDD, which again stands for total demand distortion, is a moving average of the THD based on the system rated current value, where THD is based on the fundamental current on a cycle-to-cycle basis, which changes with load. TDD uses a much longer averaging time, as long as 15 to 30 minutes, and is based on the rated current of the system. The basic definition of TDD is based on the pure and simple truth that distorted current waveforms result in increased temperature of the power delivery equipment. Hence, a time variable is introduced into the picture. The value of THD on a cycle-by-cycle basis is not meaningful when the main intent is to reduce power loss and reduce heating in the power delivery equipment in an optimal way. The 519 standard calls for measurement at the point of common coupling with the utility, but engineers specify its use at the input terminal of the variable frequency drives. This standard is often too rigorous, but it's so commonly used that it is important to address its abuse. The 519 standard is expressed as a table. An important variable described in the table is the relationship between the size of the power source and the size of the load. This relationship, called the short circuit ratio, is a measure of load current to available current. If you have a very big power source powering a very small load, the 519 standard allows you a large amount of TDD, up to 20%. If you have a small power source with a relatively large load, the standard dictates the need for a lower level of TDD, as low as 5%. Here's where the discussion comes around to the world of variable speed drives, also known as variable frequency drives, or VFDs. What kinds of harmonics do variable speed drives create? Well, the answer is it depends, especially based on the input rectifier scheme and the size relationship between the drive and the power source. Fortunately, there are things you can do to reduce current distortion on the power source, and these solutions are commonly much more cost-effective than increasing the power source's size. Mitigation step 1 is to add a DC link inductor, otherwise known as a reactor or choke, in front of the DC bus capacitors of the drive. An inductor is a good way to begin making the waveform more continuous or more sinusoidal. You can use an inductor to reduce your THD to about 40% in certain situations. Mitigation step 2 is to add an input reactor in front of the drive. An input reactor also helps protect the drive from some forms of noise and power disturbances, which is a nice bonus. This adds impedance that can bring levels of THD down to about 35%. Many times, simply adding a DC link choke in combination with either a 1% or 2% impedance input reactor is sufficient to meet TDD levels at the point of common coupling, which typically is the secondary of the main feed transformer. Another method of mitigating harmonics is to use an active filter. In facilities with large drives or many small drives, active filtering techniques can be used to help reduce THD. Active filtering techniques typically are more efficient and can be economical as well. The shunt active filtering technique adds a set of canceling harmonics back into the circuit, which are meant to counteract the harmonics generated by the nonlinear load. Shunt active filtering techniques provide the best performance for the lowest cost. However, shunt active filtering is a systems approach and requires the active filtering equipment provider to work closely with the plant manager, specifying the equipment, location, and size of the unit for installation. Another option to reduce THD is to use a variable speed drive with a 12-pulse input rectifier. This approach takes a 3-phase input and feeds it into a phase-shifting delta-delta-Y transformer. Delta-delta-Y type isolation transformers are readily available from a variety of manufacturers. The theory behind this approach is simple. The harmonics generated by a 3-phase AC to DC rectifier found in many VFDs is given by the formula H equals KQ plus or minus 1, where H is the harmonic number, Q is the number of humps per electrical cycle on the DC bus, and K is any integer. For a 6-pulse drive, that's 6 humps on the DC bus per cycle, harmonic number H yields values of 5, 7, 11, 13, 17, 19, etc. As you can see, converting a 6-pulse rectifier to a 12-pulse rectifier, that's 12 humps on the DC bus per cycle, harmonic number H yields values of 11, 13, 23, 25, etc. The 5th, 7th, 17th, and 19th harmonics are absent in the 12-pulse rectifier scheme, which results in a low level of current distortion. Now we're getting input current that is beginning to look very sinusoidal and brings us to the level of 9 to 14% THD. This approach adds a modest amount of extra cost due to the additional components of the 12-pulse rectifier plus the transformer. But in an application where a low-voltage VFD is to be connected to a medium-voltage power supply, a step-down transformer will be needed anyway, so a 12-pulse transformer used in a situation like this may not be a major cost adder. Yaskawa offers the 12-pulse input rectifier scheme standard on its A1000 drives. One step above the 12-pulse rectifier scheme is the 18-pulse rectifier scheme. 18-pulse rectifier schemes are typically found in larger horsepower VFDs and, just like the 12-pulse, require a phase-shifting transformer. Using the formula we discussed earlier, H equals KQ plus or minus 1, an 18-pulse rectifier, that's 18 humps on the DC bus per cycle, harmonic number H yields values of 17, 19, 35, 37, etc. The 5th, 7th, 11th, 13th, 23rd, and 25th harmonics are absent in the 18-pulse rectifier scheme, which results in a very low level of current distortion. An 18-pulse rectifier yields a very sine-like wave, 5 to 5.5% THD. The downside of the 18-pulse rectifier approach is that it is usually available only in large-sized drives. A typical 15-horsepower industrial drive isn't available with an 18-pulse rectifier scheme. 6-pulse schemes are most common, and 12-pulse schemes are available in some instances. Large horsepower HVAC drive applications are often held to a very strict conformance of IEEE 519-1992 and may benefit from a VFD with a 12-pulse rectification scheme. The next two configurations are non-standard and can also be effective in some situations for low-cost mitigation of harmonics. It's possible to use a hybrid. In other words, a transformer-reactor combination for either a 12-pulse or an 18-pulse design. The 12-pulse hybrid can be accomplished by putting a single delta-Y transformer into the circuit, then adding an in-phase reactor. The transformer kVA is reduced to 50% of the standard configuration. The parallel reactor is impedance matched to the transformer and sized for 50% of the load. An input reactor is optional. Similar to the hybrid 12-pulse scheme, there exists a hybrid 18-pulse scheme. This configuration requires a phase-shifting transformer sized at 2/3 the size of the drive, along with a parallel reactor that is impedance matched to the transformer and sized for 1/3 of the load. As with the 12-pulse hybrid, the chief benefit from this approach is that you will save money from harmonic mitigation. One of the most complex options for harmonic mitigation, and one of the most interesting, is called the active front end, or AFE. So, instead of the passive rectifier circuit of the conventional drive, the AFE uses an insulated gate bipolar transistor bridge, or an IGBT bridge. Schematically, the IGBT bridge is similar to the output section of the variable speed drive. The IGBTs are switched on and off to bring input power to the DC bus in a sequence that virtually eliminates the input harmonics. The THD can be reduced to 5% or less in most cases. An LCL filter is part of the active front-end design. Some AFE manufacturers add an EMI noise filter to reduce the switching noise from propagating onto the AC power line. All Yaskawa active front-end equipment uses state-of-the-art IGBTs, and an input EMI filter is optional. Yaskawa's AFE is a very reliable solution. Its chief drawback is its expense, which approaches the cost of the basic VFD. On the other hand, it offers the possibility of regeneration in addition to harmonic mitigation. Regeneration, or the ability to actively feed excess power back to the grid, can provide a significant degree of energy conservation in some applications. In short, the AFE uses IGBTs to minimize THD in a VFD. OMG, let's take a moment to review. At this point, you have a fairly good overview of the causes and remedies for harmonics. To summarize, let's take a look at the main points one more time. Harmonic analysis is a good way to quantify nonlinear loads. Nonlinear loads can be problematic. They can cause increased heat losses, noise injection, and damage to switchgear and other equipment. Excess harmonics can also cause issues with the power grid for you and your neighbors. IEEE 519 is often used and sometimes misused to establish acceptable TDD levels. It is intended for the utility customer interface, but the same levels are also applied within manufacturing facilities. Selecting the point of common coupling at the input of the devices makes analysis simpler, but it can result in unnecessary costs. By doing this, we can end up mitigating an issue that isn't actually an issue. Now, there are a variety of mitigation techniques to choose from. A standard 6-pulse drive plus DC link reactor, an input reactor, or a combination of DC link reactor and a small 1% input reactor. There are 12-pulse drives, 18-pulse drives, and active front ends. Now, while this program serves as a good start, there is still plenty to learn about harmonics. And a good place for you to continue your education is in the supplemental info section at yaskawa.com. Yaskawa. It's personal. Thanks for watching.